Good morning, everybody.
Good morning.
Let's see. We should be finishing chapter 35 today, which is interference. Next week will be diffraction, and maybe begin preparing for the test on optics, which I realize I have to write. There's always something I forgot to do. So we'll get there. We'll get there. Let's see. We left off last time. I think we finished off with the idea of what happens to waves when they bounce off of boundaries. In particular, light waves, when a wave hits a material that has a higher index of refraction, what happens to its phase? Back up. What's the phase of a wave? What day of the week is it? Sure. Wednesday is the day of the week. The phase of a wave is a way of describing sort of which way it is wiggling. Okay? And when we say that waves are in phase, what do we mean? They're both doing the same thing at the same time. Whatever it is they're doing, they're adding together. So they're peaking. If they're troughing, they're troughing. If they're equilibrium, it's equilibrium. And when waves are out of phase, what do we mean? They're canceling each other out. One is peaking, the other's troughing at the same time, and so you get cancellation. And then we talk about phase shifts of waves, where a wave can be shifted along its axis, or, in other words, we can alter its peakiness and troughiness by turning it around. So when we phase shift a wave, we turn it from a peak to a trough. So a 180 degree phase shift is an inversion of the wave. Instead, if it came into the boundary with a peak, it's going to leave that boundary with a trough. Okay? What happens when you bounce light off of a boundary where the index is less? What's the phase change there? No phase change. Okay? So upon reflection, light waves will invert or change their phase by 180 degrees if the index of refraction is higher than the material it's traveling in. If it isn't, then they'll maintain the same phase. Why is this important? Because we're going to talk and develop the rules for thin film interference, where we have a thin film of material, different index of refraction than the substrate or the material the film is sitting on, and also different from the material that the light ray happened to be traveling in, the incident ray happened to be traveling in. Now, we're going to draw this picture over and over and over again, or something very similar to it. I actually have a slightly simplified version of it. But we are going to make a concession for Physics 4C to keep this easier. We are only going to treat normal incidence waves, meaning that all of our light rays are going to be hitting at 0 degrees to the surface. Remember in optics, what is 0 degrees? Straight up and down. Okay? When you draw a picture for something that's hitting straight up and down, okay, the light ray comes in. Does it reflect? When light hits a surface, does it reflect?
Yes.
Yes. What direction? What's the angle of reflection? If your angle of incidence is 0, what's your angle of reflection? 0. So the reflected ray goes right back up. But reflection isn't the only thing that happens. There's also transmission, meaning that part of the wave reflects and the other part keeps going through the material until it hits the next boundary. What's going to happen at the next boundary? There's going to be reflection off of this one, which goes right back up and leaves, okay? and then there will also be transmission. You see how confusing it is to draw it the way it actually is? You just draw a straight up and down line. All your lines are on top of each other, and it becomes horrible. So instead, what we do is we draw these kinds of pictures. We know the light isn't doing this, okay, because we're doing straight up and down. But in order to keep track of what's going on, we have our incident ray. At the surface, it reflects, but also transmits, going through the material. It then bounces off the bottom, reflection, and comes out. But then there's also another transmitted ray. So lots of things going on here, but we're going to draw it as if it hit at an angle, so that we can keep track of what each ray is doing. But we're always going to assume zero angle of incidence. And the reason we're doing that is because if we didn't, we'd have to find the angles of refraction in the material. And our path length difference would get pretty complicated with trying to find the Pythagorean theorem, blah, 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 lengths of travel through that thing. What's the path length difference if the ray comes down, strikes the surface? If the thickness of the film is t, what's the total path length difference for the one that bounces off and comes back up? Yeah, the path length difference is 2t. So that's a lot easier than having to go through and do all of the Pythagorean theorem. It's not impossible, but it's the concession we make for physics 4C. All right, so let me try. There's a lot of things to keep track of here, okay? A lot of rules, a lot of setups, but I want to take you through several setups. We're not going to actually calculate anything to begin with. I just want to take you through several setups so you get an idea of what is happening, okay, in these films. So, we're always going to draw a structure that consists of a thin film. The film exists between these lines. And so there's going to be like N1, N2, and N3. These are going to be different indices of refraction. So for purposes of helping you learn this stuff, I am going to say that I'm going to give you the index of refraction of these things. So here's 1, here's 1.5, and here's 1 again. So this looks like it might be a thin layer of glass that's surrounded by air on both sides. Okay? All right. We need to develop the equations for interference for this structure. And we've done this with the double slit, that whole process that I took you through, where we found the path length difference and we set it equal to a condition. So we're going to do that same thing again, although we already know what the path length difference is. And what we're going to do is we're going to draw. This is how I draw it. I draw it bouncing off. And then I just kind of continue that and draw another one bouncing off the bottom. I don't try to do like refraction angles or anything in here, okay? Keep it simple. This is a visual hook to help you derive the conditions that we're going to have, okay? So you draw both of the bounces off the top interface and the bounce off the bottom interface. And the next thing you do is you determine the phase shift of those reflections. So the top ray reflected off the top. How did it reflect? What is its phase change based on the indices of refraction in this situation? 180. Why do you say it's 180?
Because it's higher.
Because it went from an index of 1 into an index of 1.5. And the rule is that if you go from low to high, you're going to invert your phase. So that means that this reflected ray is 180 degrees different in its phase from the incident ray. The transmitted ray doesn't change its phase. It's only the reflected one that changes its phase. So the one that goes into the film is at 0 degrees phase change still. And then it comes into contact with another interface. Only now it's traveling in 1.5 and it's trying to get into 1. So what's the phase change going to be if you go from high to low? 0. No phase change. And so that's what you're going to put on the second ray. You're going to label these rays based on the physics of how light is interacting at the two different surfaces. I didn't draw the ray that goes down through into the next one. You can safely ignore that one. It's not important. Okay? What's important is keeping track of the phase changes at the top and bottom of your film. You must do this every single time. Okay? You're going to draw this picture, and then you're going to determine what the phase changes are. All right. We are trying to figure out what condition will cause constructive and destructive interference. And remember, in interference, we always set a path length difference equal to some sort of condition. The second ray traveled an extra distance through the film, and if the film thickness is t, then the path length difference is 2t. The condition. What are the two conditions that we can set? Think back to the two-slit interference problem. What were the two conditions? Like mathematical expressions for the conditions. It was m times lambda, the wavelength, or it was m plus a half, referring to full wavelength shifts, so 360-degree phase shifts for m lambda, or what does m plus a half lambda mean? 180, right? So m lambda and m plus a half lambda, right? Refer to these different shifts, okay? This one is 0 or 360 degrees. This one is 180 degrees out of phase, okay? So if we cause the second ray, the one that bounces off the bottom, interface, if the distance, the extra distance it travels is equal to an integer multiple of this wavelength, then what will those two waves do? The first one is 180 degrees out of phase with the original. The second one is 0 degrees out of phase with the original. And we're saying the thickness, the path length difference, will cause no change in the phase. So what are those two rays doing right there? One of them 0, one of them's 180. They're canceling each other out. And therefore, we have what kind of interference? Destructive interference. But Mr. Balogh, when we did the double slit, m lambda meant constructive. I know. It's going to get worse. Hang on. The other condition, m plus a half lambda, we're saying that we're going to tune the thickness of this material so that the path length difference is equal to a half integer multiple of the wavelength. Meaning, when it travels that extra distance, it will shift its phase by 180. So by saying m plus a half, I'm saying change the phase of the second ray by 180 degrees. If we change the phase of the second ray by 180 degrees, and the first ray is already 180, they'll both be 180. And so therefore we will have what kind of interference? This is hard. It's hard. You've got to do the concept and work through it. And the way you're going to learn how to do this is by practicing a lot. So let's do it again. This time we're going to have 1.3, and 1.5. So maybe we've got a thin layer of oil or water. sitting over the top of glass. Just as an example. Okay? So first ray bounces off, second ray bounces off. Again, it's not a technical drawing by any means. It's just a visual anchor. Turn to your neighbors and tell them what the phase changes are for both of those reflections. Go. All right, what's the phase change of the first one? 180. Why? Low to high, right? 1 to 1.3. Okay, what's the phase change for the second one? Also 180. Good job. Okay. Path length difference equals condition. The path length difference is 2t. The conditions can be m lambda or m plus a half lambda. What does the condition m lambda mean? Don't go for constructive or destructive. When we say m lambda, what are we trying to say? We're not going to change the phase of the second ray. The path length there is equal to an integer multiple of wavelength, which means we're going to keep this relationship as is. So this 0 or 360 as is, or keep it the same. Okay? So what does m plus a half mean? Change it. Right? And how much are we changing it? By 180 degrees. So if we keep it as is, we don't make any changes to what's naturally already occurring, what kind of interference are we going to have? Constructive. And what the second equation says, add 180 to the second ray. 180 plus 180 is 360. And when you put 360 and 180 together, what do you get? You cannot rely on the equations to tell you what's going on, because the equations will change their meaning. Problem to problem, situation to situation. Do not think, don't fall into the trap of thinking m lambda always means constructive. It does not. For double slit interference, it does. But for thin films, you must derive the meaning of these equations. Equations are given. It's 2t equals m, right? Okay, those are given. But whether they are the constructive or destructive equation is going to depend on the physics of the film. So what are the steps that you go through in order to figure it out? Draw your picture. And with your picture, you're going to do the phase changes, right? Second step, you're going to write down your equations, and then you're going to derive what the equation is telling you by looking at m lambda and m plus a half. You can always count on the thing I've written over here on the right-hand side. M lambda always means don't change a thing. Keep the relationship as it naturally exists in the problem. n plus a half always means change the second one, change its phase by 180 degrees. You then go back to your drawing and determine what, if we keep things the same, or if we change things up, you determine what then the equations mean, constructive or destructive. Yes?
We only change the second one, or do we also add the one?
No, the add 180 only affects the second ray. Because it's the second ray that has the extra path length difference. It's the one that's traveling through the film. Okay? So you can step back a little bit and say, okay, m lambda means I'm not changing anything. I already know they're 180, 180. It's going to be constructive. n plus a half means I'm going to change the second one. I'm going to add an additional 180. So now I've got 180 and 360. Okay, that's destructive. In the first case, it was naturally destructive, wasn't it? And so m lambda, keeping things the same, would mean destructive. M plus a half, adding 180, would bring them into phase, causing them to be constructive. You have to do that every single film. There is no master list of like, I mean, you could do all cases, right? But like, you want to go through the diligence of doing it every single time.
So we're never going to add 360 on the two initial ones?
No, it's going to be 0 or 180.
It's just going to add up to 360.
Right, when you change the second one by 180, it adds up to 360, which is a full phase shift. You could also label these as half lambda and lambda. We tend to use degrees when we're talking about phase shifts. Okay, there's one more piece here that you need to know about, because I didn't lie, I just shoved this under the rug a little bit, and we got to come back to it, okay? The wavelength of light changes in a material. The frequency does not. When light passes through a window, when red light or blue light or green light, any color light passes through a window, it stays the same color. And the frequency of light is what determines its color. And so therefore, when you have the relationship, right? Speed of a wave is equal to its wavelength times its frequency, basic wave mechanics. If the frequency stays constant for transmitted light moving through a material, does the speed change in the material? Yes, that's the whole point of index of refraction, isn't it? Remember what index of refraction is? Speed in a material divided by the speed of light. It's like a ratio. Okay? So, other way around. Ratio of the speed of light to the speed in the material. It's got to be a number always bigger than 1. Okay? So light slows down when it gets into a material. That's why it refracts in the first place. So if the velocity is equal to wavelength times frequency, and the frequency is a constant, but the speed changed, the other thing that has to change is the wavelength. So the wavelength in any material, lambda sub n, so the wavelength in any material that has an index that's not 1, because 1 is space, right, is going to be equal to the wavelength in vacuum divided by the index of refraction. Now, why am I talking about this? The path length difference, the extra distance the second wave travels through the film, needs to be a multiple of the wavelength as it is in the film, in whatever material it's traveling in. So if it strikes with 600 nanometer wavelength, that wavelength is going to change. In fact, it is going to be lower in the film than it would otherwise. That means that the conditions we have here have to, don't do this, don't write this in your notes, have to be lambda sub n's. It's the wavelength in the film. But that means that for every one of those lambda sub n's, we got to divide it by n. Don't do this either. Okay? So physicists don't like fractions. So what we tend to do is we write our n's in there. You can write those in. The equation should be 2nt. 2 times the index times t equals m lambda. In writing it this way, in having these equations written like this, you can use the wavelength that is given to you in the problem. So when they say light at 530 nanometers strikes a puddle of oil or something, right? They're giving you the wavelength in air. That's the wavelength you use. You don't have to go and find the wavelength in the material. It's kind of baked in, right? 2 times the wavelength of the times the index of the thin film times the thickness of the film equals m times whatever wavelength they gave you in the problem. But it's an important thing you have to correct.
But it doesn't change like the process of it.
Does not change the process that I taught you. Okay? It's just we need to recognize that the wavelength changes as light moves through materials, and that means the path length difference depends on the wavelength in the material. So we have to include the index of the material somewhere, and we physicists like to draw things all on one line.
JT was used for all right? Not just this specific.
Correct. Path length difference. This is wrong. I always think of the path length difference as 2nt. It's 2t. But I don't want to have to go do extra stuff to figure out the wavelength in the material. Because it's important, but I know the wavelength that struck the thing in the first place. Let's reference everything to that. Okay, let's do some examples. And yes, you must derive every single time. You are deriving, not the equations. The equations are there already. I mean, every thin film problem is going to have 2nt equals m lambda and 2nt equals m plus a half lambda in it somewhere. You're going to be using those. What you don't know at the beginning is which one is constructive and which one is destructive, and you have to derive that meaning. You have to go through the conceptual steps, and I know how much you guys love conceptual questions. It's the only thing. If I put 12 conceptual questions on the exam, you would be perfectly happy, right?
Those are almost worse sometimes.
Yeah, I know. Trust me, I know. And so why do I keep giving them to you? They're the important ones. They really are. Okay? And it hurts my soul every time I go on to Wiley Plus and I see that people took 1 minute on those first 3 questions I give you on the homework. I know it's easy to get those right, to get 100% on those, right? But if you really dig into those questions and you master the concepts there, you're going to be smooth sailing when it comes to the homework and the exam. I know some of you don't believe me because you're like, I spent all that time, Mr. Bill, I still don't understand. Good. You're on the right path. You have the rest of your life to figure it out. Well, actually, until the test. All right. What's the picture look like? It just looks like 2 lines, right? Okay. And then you draw 2 bounces. Okay. It can be messy, right? Doesn't have to be real clear. Try to get from the information in the problem what the film is, right? In this case, what is the thin film? It's soap, right? And they gave me the index, 1.33, which is exactly the same as the index of water, because that's what bubbles are. They're mostly water with a little bit of soap. Okay, so the index is 1.33. Okay, this film is in air. So what is on the top and bottom of the film? 1. Okay, so you're setting up the structure, right? And now what are you going to do? Your phase shifts. What's the top reflection's phase shift? How'd you do that? Went from 1 to 1.33. Okay, what's the phase shift at the bottom one? 0. Okay, so if we write down 2nt equals m lambda, what are we telling the physics of the problem to do? Don't go straight. Don't. I know you want to go straight for constructive or destructive. 2nt equals m lambda means keep this the same. This relationship, as we've drawn it, stays the same. So if it stays the same, then what kind of interference will we have? Destructive interference. What does 2nt equals m plus a half lambda mean or say? Change the second one by 180. So then we will have 180 and 180. And both of them being 180 at the same time. All of that needs to take place before you even begin to figure out what the problem's trying to ask you. Now I will go and look at what the problem's trying to ask me. Okay, it's asking me two things. What thickness? So what are they asking me to solve for? T. They're asking me to solve for T. Will produce constructive interference upon reflection. Which of these equations am I going to use for part A? I'm going to use m plus 1/2 for part A because they're asking me about constructive interference. So 2nt equals m plus 1/2 lambda, and they asked me to solve for the thickness. So I'm going to go ahead and solve for the, okay, all right, okay. What's n? Good. It's the film's index of refraction. It could be easy to get the wrong index in there, right? Because some problems will give you 3 different indices. So make sure you understand what you're putting in the film's index. I'll show that in a minute. We're looking for a T. Do we know the wavelength?
Yeah.
Yes. What's M?
0.
There? Okay, so if I solve this for thickness, right, I just come over here and it's lambda over 2n times m plus 1/2, right? That means that this thickness can come in multiple values. Kind of the whole point, right? The thickness can be, as long as it's a half integer multiple of this, right, I can get the kind of interference that I want. But the problem is asking me for a specific thickness. Which thickness? The minimum thickness. So what's the value of m that we choose here in order to get the smallest thickness? 0. If I choose m equals 0, okay, to minimize the thickness, then I'm going to have T equals lambda over 4n. Whoa, what just happened? 0 plus 1/2 is half. And 1/2 times lambda over 2n is lambda over 4n. Okay? So I put in 652 nanometers divided by 4 times 1.33. Again, the index of the film. And I would get 122.6 nanometers. I mean, I could have put in e to the minus 9 or whatever, but I got to regulate the nanometers. I'll keep it in nanometers. What's the units of index of refraction? No unit. It doesn't have a unit. So, all right. So there, I found the minimum thickness this needs to be in order to have constructive interference. Okay. Part B. What visible wavelengths, plural. Ooh. So how many answers am I going to have? Maybe more than one. Okay, 1 or more. Will destructively interfere from this film. So the implication being that if we use that thickness right there, right? So which equation am I going to use? I'm going to use 2nt equals m lambda. Because that's, for this problem, for this situation, that is the destructive equation. I'm solving for wavelength. So that's 2nt over m. Oh, this is kind of interesting. So I have 2 times 1.33 times a thickness of 122.6 nanometers all over some thing, right? So this turns out to be 326 nanometers when you do 2 times 1.33 times, right? Okay, all over m. Okay. So what is m? Like in our problems, what values does m have?
Integer.
It's integer. 0, 1, 2, 3, 4. Can you put 0 in here? No. Okay. So for the m lambda case, never use 0. Start at 1. Okay. So if we put in 1, m equals 1. Okay. For m equals 1, t would be what? It would be 326 nanometers. And for m equals 2, what? In my head, it was correct. Okay, thank you. Lambda 1, 326. What would lambda 2 be?
163.
Yeah, like 100. Yeah, it's actually 163 is the answer. Okay, and for m equals 3, what's going on here? It's getting smaller. Okay, now the visible portion of the spectrum. And physicists fight over this all the time, so this physicist is going to say that this is the correct values. The visible portion of the spectrum is 400 to 700 nanometers. Do any of these wavelengths exist in the visible portion of the spectrum? No. So what's the answer? None. There are no wavelengths that exist in the visible portion of the spectrum. If we had gotten, say, lambda 1 of 1,200 nanometers, well, that first one wouldn't, right, because it's outside the visible range. The second one would be at 600, so that one fits. The third one would be at 400, so that fits, right? So there would be 2 that fit in the visible range. We can get multiple wavelengths that constructively or destructively interfere in these films because you can have different thicknesses of film. So for soap bubbles, why do they have colors at all? This thin film, what's the light doing? Bouncing off the top, going through, bouncing off the bottom layer, and then constructively and destructively interfering with each other. Reds for reds, blues for blues, greens for greens. We're not seeing it at a normal to the surface, we're seeing it at angles, so the angles throw in a different additional complication that you guys don't need to worry about. But the point is, different wavelengths will be constructively or destructively interfered for different thicknesses of that bubble's film. And that thickness does change depending on where there's more soap. Like the bottom of the bubble tends to be thicker than the top part of the bubble because gravity is pulling the water and the soap down. So all of that complexity of thickness, variation of thickness and variation of angle is giving you different constructive and destructive interference, sometimes killing red so only you see blue, sometimes making red the dominant thing so you don't see any of the other colors, and everything hits your eye in that beautiful cacophony. Ooh, there's a big word. What's cacophony mean? Noise, sound noise. Okay, you get visual rainbows coming from everywhere. All right, let's do it again. What I want you to do right now is with each other, with your neighbors, I want you to draw the picture and determine which equation is for destructive and which equation is for constructive in this particular problem. You don't have to go any further than that. You don't have to figure out what the problem's asking you. Just set up. Do it together. Talk to each other. Talk through the process. Go.
Remember how he said soap was the same as water for the glass problem?
All right. How'd you do?
So far.
We okay? Who's lost? Like who's not sure what's going on? It's okay. This part is probably like maybe the easiest part, so to speak. Okay? In terms of like it's concrete. Like change the index. If it gets higher, I know it's 180. I may not know what 180 means, but I know it's 180. Right? So now we have to figure out what these equations are telling us, like which one applies to which situation. And what does 2nt equals m lambda tell you to do? Keep that relationship the same. That relationship staying the same would be constructive, because they're the same phase. The second equation is telling us change it by 180. Add another 180 onto the end, making it 360, right? It's like it comes in here, whoops, and adds 180 to be 360, right? And if I did that, I would now have different phases. So what would different phases do? Cause it to be destructive. Okay, that's the derivation. That's like the setup, the visualization.
You have to keep all like the, I guess, all the index and refraction. Like in my notes,
I'll give you. You can always ask me for an index refraction material, unless the problem's asking you to solve for the index. But I'll give you, like, if you don't remember the index refraction for water, I just give it to you. Like in this problem, I didn't give it to you. I gave it to you last problem. I have like several of these memorized because I've been around index refraction so much. All right. So, what does the question now want to know?
So I want you to find the minimum thickness, right?
Okay, so it's asking for thickness, but which I got two equations I can use. It's absent. It's using words to give me a clue as to what's going on. So if something is absent, what kind of interference is it? That's got to be destructive, right? So I'm going to use 2nt equals m plus a half lambda to solve for this thickness. They're asking me for minimum thickness. So what's the trick for minimum if I have m plus a half? I just make it 0. If I have m lambda, what's the minimum? 1. Don't put 0. Yes, a thickness of 0. So solving this for thickness, it's going to be lambda over 4n if m equals 0. And so let's see, that is 521 nanometers all over 4 times 1.25, which gives me 104.2 nanometers. Yes?
If we're talking about the second refraction, how come we use the M when it was in the air? I mean, the lambda when it was in the air, and the N when the oil. So, would not.
Because the wavelength changes in the film, we use the index of the film in our derivation. But, so to avoid having to take 521 and divide it by 1.25 and putting it into our equations, we just put the 1.25 on the other side. Physicists are weird.
So our focus here is for the first one or the second one?
Both. You have to be keeping both in mind. The index in that equation is the index of the film, and the wavelength is the wavelength, the incident wavelength. Whatever the wavelength was as in whatever material it was in. So if it went from glass to oil to water or something like that, you'd use the wavelength in glass in this equation. Because they would have to give you the wavelength in the glass. It's incident wavelength and index of the material. Why would you ever want to do that? Why would you ever want to know the thickness of a thin smear of oil on water?
Oil spills.
Oil spills. What's one thing that's really critical to know in an oil spill?
Volume.
How much oil is in that spill? Because that's going to determine how much stuff you're going to need to contain that oil spill and clean it up, to mitigate it. And so how do you find out how much oil is in your spill? Well, oil is lighter than water. It has a tendency to go to the surface. And so if you can somehow measure the thickness of that oil film on the surface of water, maybe at 100 points, maybe at 1,000 points, maybe there's a device that can shine light onto this surface and read what the destructive interference is, the wavelengths that are absent in the return. And from those wavelengths, give you a thickness of the oil right where that sample was taken. And then you do that at 100 different points on the oil slick, and so you come up with an average. And now you have an average thickness, and you have an average area because you can take pictures or send out boats or whatever, right? Okay? So you know area, you know thickness. Now what do you know? Volume. To a fairly good approximation, and now you'll know how many surfactants you'll need. Those are chemicals that break up oil. How many bacteria, volume of bacteria needed to eat that volume of oil. Did you know that we use bacteria nowadays to clean up oil spills? Because the bacteria go out and consume the oil. Okay? Use it on your driveway? Yeah. Some of these enzymatic and bacterial cleaners are fantastic. They get rid of the stuff and they're great for the environment, right? So, and the bacteria don't affect humans. Yeah. Always got to give that existential dread. But they're great. So that's a direct application of this kind of physics. We're doing the very tippy top of this, right? Okay? Because it's a lot more complicated when you're doing it not normal to the surface. Okay? You got other things that you need to take into account. But nonetheless, okay, it is that. So I want to take a little bit of not a tangent, okay, but I want to detour, sure. What you're looking at, okay, is what I did in graduate school. Not this simple, of course. I did the hard stuff, right? Okay, and the reason that I went into it, okay, is because they promised me that I would be able to work with NASA, and they didn't lie, okay. So my master's thesis, if you come to my office, I can show you my thesis, okay? My thesis was actually written on how do students learn physics in college? And it's more than 100 pages of analysis of how students learn. I had another thesis, which I don't have in my office anymore. I can't find it anymore. Apparently it wasn't that important. Where I detailed the research that I was involved in extreme ultraviolet physics. What I did is I specialized in how light that is in the extreme ultraviolet portion of the electromagnetic spectrum interacts with materials. Specifically, how do you get extreme ultraviolet, fancy way of saying X-rays, but when you say X-rays, everybody thinks medical X-rays. We were not using medical X-rays. We were using what exists between ultraviolet light and X-rays. Okay? It was this no man's land where people didn't do research because it was hard. And so there's degrees there. Okay? And so you go looking for it. And I was told that if I learned how to do all this stuff, I could go work with NASA. Because NASA wanted to fly a satellite that took pictures of the Earth's magnetic field. Those of you that take in 4B. Okay, what's a magnetic field? It's a conceptual idea. It's a pattern of forces that exists because the Earth has this magnetism to it, and you put another magnet near the Earth, it responds to that magnetic field, the pattern of forces. Is the magnetic field visible? So imagine when one of my advisors goes to a conference in extreme ultraviolet optics, and NASA is at the conference, and they're asking people at the conference, hey, how do you take a picture of a magnetic field? The physicists go, wrong question. Okay? Because what is the right question? How do you take pictures of the things that are trapped in the magnetic field? You can't take a picture of a field, but magnetic fields trap charged particles. And what's the biggest source of charged particles in our solar system? The sun. And so if you can take a picture of the charged particles that are trapped in the Earth's magnetic field, you will then have a picture of the Earth's magnetic field. And so that's where the IMAGE project was born. The IMAGE project was a satellite that would have 6 instruments on it, all doing different things, that would take pictures of the Earth's magnetosphere, the sphere of influence where the magnetic field of the Earth is dominant. It was a trash can. It was designed to be cheap. It was designed to be fast. It was designed to have it's kind of as few moving parts as possible. And as part of one of the 6 instruments that's on this satellite, and I know it's got 8 sides, okay, right? But so this is like there's instruments here and there's instruments there and all that kind of stuff, okay? That one's mine. This satellite was several different schools and the Southwestern Research Institute, which is like a private government-funded research institute that does a lot of work with NASA as a contractor. Anyway, we all came together and said, how are we going to do this, right? And there were different things. So the task, the challenge that our research group was given was take pictures of 2 very specific hydrogen ions, okay? Take a picture of an ion. Okay. So this ion must emit some sort of radiation, visible, not okay. Turned out it was in the extreme ultraviolet portion of the spectrum that these 2 ions live. Their emission spectrum were in. And unfortunately, there were a lot of other ions that had a whole bunch of them. And there was one dominant one that threatened to sort of wipe out the signal of the one that we wanted, the 2 that we wanted to track. And so we had to develop a telescope mirror that would selectively cancel one wavelength and magnify or enhance 2 other wavelengths in the ultraviolet portion, the extreme ultraviolet portion of the spectrum that nobody knew anything about and basically behave like X-rays. How well do X-rays bounce? No, they don't. X-rays go through stuff, right? Okay, they get scattered by minerals and things in your bones, but they don't bounce. And so, how do you make a telescope, a lens, or a mirror that can focus X-rays into a picture? Magnets take too much power. There's a power budget on every satellite. You got to live inside of it. So the best bet is to make a telescope that has a mirror in it, and the trick becomes, how do you bounce X-rays? Answer, thin films. Constructively interfere the wavelengths that you want to constructively interfere. Destructively interfere the wavelengths you want to destructively interfere. Oh, and you only get 1 bounce. Because after the first bounce, the signal is so attenuated that the detectors can't pick it up anymore. Southwestern Research Institute went to Intel and said, hey, can you make this happen? And Intel's like, no. Why would they ask Intel? Because Intel specializes in extreme ultraviolet optics because that's how you make computer chips. You use those wavelengths to make smaller and smaller features on the silicon. And so they knew a ton about extreme ultraviolet optics, but Intel said no. So they went to AMD. AMD makes chips too, right? So how do you do that? They went to TSMC. They went to all these places. They're all like, no. They went back to Intel and they said, well, could you research it for us? And Intel said, sure, give us $10 million. And we'll let you know in a year that it's impossible. So my advisors are listening to this conversation going on, and after it was all done, pulled the Southwestern Research Institute aside and said, hey, we'll do it for you, and we'll do it for $100,000. What? Because it turned out at BYU, we were in this unknown land. We were trying to measure stuff in this area that nobody knew anything about. And my advisors thought it was possible. They weren't sure. So Intel's asking for 10 million. Why are you asking for 100,000? They said, well, we have 10 graduate students that we would like you to pay for their education. So we'll take $100,000 for the school, but you have to promise to pay these graduate students for their degrees. Southwestern Research Institute said, you're on. And the 10 of us got our graduate degrees paid for. I paid $0. Now, all of the intellectual property I developed is owned by the Southwestern Research Institute, right? Okay, but I got a master's degree by paying this amount. They paid for my books, they paid for my pencils, they paid for my tuition, they paid for my living expenses, they gave me a food stipend. Go into STEM. Seriously, like, English grad students pay through the nose and have college debt for the rest of their life. STEM students go to graduate school, and usually you're hooked up with some sort of research that's being paid for by a corporation or the government, and you get your degree paid for. Anyway, it's definitely like, people are like, oh, STEM is so hard. I'm like, it's the easy road. Like, seriously, it is the easy road. Anyway, we built this thing. It launched. The building of it, oh my gosh. We thought we could do it in like 9 months. We gave it to them at 18 months. Okay? And we felt so bad because we thought we were holding up the whole thing. Well, it turns out that they needed like another 12 months past when we turned in our thing, because there was some delays on there. Unfortunately, while we were developing this, the space shuttle Columbia re-entered the Earth's atmosphere with a hole in its wing and burnt up and killed all the astronauts on the inside. And so NASA stopped all of their launches for a period of time to make sure safety things. And our satellite, which was supposed to go through like the bare minimum number of safety checks, because honestly, if it blew up, we could just build another one, right? Ours had to go through the space shuttle's human flight testing. Yeah. I was having kittens because we didn't design those telescope mirrors to be, right? We designed them for the shaking of launch. We knew those parameters, but the shuttle, like the human flight, they're even harder. So they took our satellite, they threw it into an oven, and they baked it, and they shook it, and they spun it, and we were convinced it was going to just be nothing when it got to orbit. Anyway, we got to see the launch, Delta II out of Vandenberg Air Force Base. It was incredible. I am about to show you a picture that I'm not sure I want to show you, but I'm going to show it to you anyway. Because it reminds me of how old I am. Okay. Picture me in grad school. Okay. Simon, Matt, and Jorge. We were the main graduate student leads on this project. We all had sort of different roles. Matt, the one standing next to me, was responsible for measuring. Like, we would develop a film, and did the film that we put down actually meet the parameters that we were going for? I was in charge of actually making the films. That was my specialty. Jorge and Simon both were on the sort of theory side, the programming, how do we develop what materials you need to put together in what order in order to make all of this happen. And realize, in a single film, we had to destroy one specific wavelength and constructively interfere 2 others. We did it by using something called multi-layered thin films. It's a bit of a cheat. But basically, instead of just one film, you stack films on top of each other. And you take advantage, and I drew these all the same thickness, but you take advantage that the light is going to bounce off of multiple layers depending on how thick those layers are. And if you can play a game with attenuation and really eke out some of the, because it gets less and less on every bounce, right? You can play this game. Anyway, and I think I already kind of told the story about how we discovered that by mistake that it was the oxide layer on the top that really saved our bacon. Anyway, a lot of stuff that went into it. I'm holding not what would be the mirror that goes onto the device. It was a sample. It was a blank. It was like we would practice laying it down first on silicon chips, little tiny pieces, and then we would do it on the actual mirror structures themselves. That picture down there, the person doing the article thought it would be cute if we were all reflected. It turned out that the materials we're using happen to be reflective in the visible portion of the spectrum. But for a certain X-ray, this mirror looks like a black hole. And for two other X-rays, it looks as bright as the sun, right? Because the layer is able to both destructively and constructively interfere simultaneously. Anyway, we did it when Intel and AMD thought it was impossible. But they paid for my, or Southwestern Institute paid for my degree, so. And the pictures we got. This is a picture. So the circle is the Earth. Okay. You can see the aurora. See the circle inside the circle. Okay. That's the aurora borealis, the northern lights, and the magnetosphere around the Earth. It turns out that the Earth's magnetosphere is wonderfully complicated and is not at all that teardrop shape that they always draw in books. Okay. In fact, there's times when that drainage plume, the picture they draw is like of the solar wind blowing the magnetosphere backwards, okay? Sometimes that point of the magnetosphere is actually pointing towards the sun. It's really cool. It kind of wraps around and flips and does all these kinds of things. Okay? As a matter of fact, in this picture, the sunward side is over there, right? So here the plume is pointing back towards the sun. Excuse me. This is a time lapse of pictures that were taken by the telescope. Okay, showing how the magnetosphere evolves. Again, we're taking pictures of the particles that are trapped in the Earth's magnetic field. So this is the closest thing we're getting to a picture of the magnetic field of the Earth. The reason you see sort of the double lines down through this thing has to do with that we actually put 3 of those telescopes in the device and stitched the pictures together. Atlas.
If you hadn't been able to successfully block out the one particle or ion that was canceling out the other two, would you have not seen anything?
Yeah, so there was sort of we had a ripcord a little bit in that in front of our telescope they were able to put a window that kind of canceled out most of what we weren't looking for. And so had we not been able to make the film the way they want, the ultimate thing. And by the way, we had 15% as our maximum reflection, right? The people making the camera that would collect the light told us that they could get away with 5%. If we had as little as 5% reflection, they would still be able to get useful data out. So the fact that we managed 15%, 3 times the amount of information that they needed, is great. We could have gotten by maybe with another window, which would have cut the light down even more. There were some other tricks, but the ideal was really to be able to do that. You don't go into making things like this and not have like a 90% surety that you can do it. Anyway, this the image satellite was the first of the satellites that was used to do space weather. You can now go to spaceweather.com or gov or whatever it is and see the space weather forecast. The image satellite did make it onto the cover of Science magazine, which is one of the leading places for scholarly work. Let's see, where is it? Somewhere in here. Made it on the cover, but there we go. Made it on the inside too. Okay, these are different instruments that were on the satellite. Here's ours. right? Okay? And so if you come here and you look at the references and notes and everybody that they thank, okay, my name is mentioned exactly 0 times. Okay? Because we were graduate students. But we got stickers. Lockheed Martin apparently built the vehicle that it was on, right? Okay. I always love these when you get newspaper clippings. Okay. So there's that picture I kind of showed you down there in the corner, right? Okay. I have a number of newspapers. You come into my office, you'll see one of me and Mr. Balogh blowing stuff up for the science show. Okay. Without fail, there's always a headline on the page. Okay? Some big headline. The one in my office, Mr. Balogh and I are having tons of fun, blowing up balloons, big explosion. The headline right next to that one is Meth Lab Found in Fresno. What is this? You are looking at the surface of a compact disc. And by extension, a DVD. It would look similar, just it would be smaller. Okay? So these are what we call pits in the surface of an optical disc. And why am I talking about them now? How do DVDs and CDs store and read information? The answer is by using interference. Constructive and destructive interference is what has the ability to read and write information onto these surfaces. A laser beam bounces onto, and so this is kind of upside down, right? Like when you put it in your player, it actually reads it from the bottom up, okay? And so a laser beam comes up from the bottom, and if that laser beam hits one of these pits, okay, pit as seen from above, the width of the laser beam is kind of like actually 2, okay? And you see here how it's like right on the edge? So one of those beams is bounced and has a shorter distance to travel than the beam that went into the anti-pit, okay? And that means that those two, the reflected beam is either going to be in phase or out of phase. In this picture, it's out of phase because the pit depth, the feature size on the CD, is tuned to be exactly a quarter wavelength of what's being used to read it. Why a quarter? Because if you go quarter up and quarter down, what do you get? Half. And there's your destructive interference. So when the beam strikes on the edge, you get destructive interference, and the device knows that you're going from a pit to a trough, and so therefore you're going from a 1 to a 0. So there's another device that reads the reflected beam, sees flashing laser light, on, off, on, off, on, off, and what do you assign to a brightness? What do you assign to a darkness? You just store digital information.
So it's a metal layer.
Yep.
How, like when you burn the CDs, how does that?
It's scribing. It's putting features, pushing and pulling that metal layer in and out. We call it CD burning for a reason. You're burning it into the surface. The one that's really crazy is the rewritable ones. Like how you can go back and redo it.
Is solid state similar or is it completely different?
Very different.
Does it involve optics at all?
No, it involves quantum mechanics.
Oh.
There's one more thing I need to teach you, and what time does this class get off? In 4 minutes? We have till 10 till? I always think it's 45, but okay. We'll take 5 minutes. There's one more thing to teach you, and this is what we're going to do next week in lab too. So we're gonna get it down and dirty into the details of this in lab. Okay? But conceptually, interferometry is using the interference of light to measure very precisely the distances to things. In this setup, light, usually a laser, is shined onto a beam splitter. This is a piece of glass that's partially silvered, meaning that 50% of the light passes through while 50% is bounced off. So you literally split the beam into two parts. One bounces and goes off to a mirror, the other one goes through and goes to another mirror. Those mirrors bounce the light backwards and they join up, and you look through a telescope at how they join together. So two beams traveling down two different legs of the interferometer coming back together. If those two beams go exactly the same distance back and forth, what kind of interference are you going to have when they get back together? It's going to be constructive. If one of those path lengths is equal to half the wavelength, in other words, the mirror moves a quarter of a wavelength, because remember it's a bounce, so it's got to go in and out, you'll get destructive. And because it's an interferometer and it's going through circular apertures, you get circular interference patterns. Not the linear ones that I've been showing you, but these actual circles. So we're going to be making these in lab with an interferometer, and you're going to be counting how the pattern changes as we change a mirror distance. So at 600 nanometers, let's do 600. At 600 nanometers, this means the interferometer can track, at a minimum, a quarter of that wavelength. What's a quarter of 600? 150? That means in lab, you will be able to measure a distance change of 150 billionths of a meter. A factor of 1,000 smaller than the human hair on a device that sits right on the tabletop. We're going to use that to not only determine the wavelength of light in the interferometer, but also to be able to measure the index of refraction of air. And we'll explain how we're going to do that later. This is quite possibly the world's largest interferometer. That's a building. That's a road. That's a building. Okay? And those are the interferometer arms. This is the picture of the interferometer that exists in Washington State. It has a cousin, an identical facility in Louisiana, and I believe 3 more spread all over the world. They all do exactly the same thing. They measure the change in the length of one of the interferometer arms down to a precision of 1/10,000th the radius of a proton. These things are so sensitive that they can measure the rumble from cars going down the highway on the other side of the planet. What is this for?
Gravity.
This is for finding gravity waves. This is LIGO, the Long Base Interferometer Gravitational Observatory, or something like that. Okay? We'll talk about how LIGO works and why gravity waves are amazing in lab on Tuesday, where I will show you how to use the interferometers. You have a packet. It's 14 pages thick on how to use an interferometer. Read it! Be familiar with the terms in it, because there's a whole calibration routine you're going to have to go through before you can even get data. So it's a great lab, and we'll talk more about how interferometers work when we get there. On Monday, I'm starting the last chapter, chapter 39. No, 36. Because a 6 is not a 9, but it is upside down. See you then.
Is the image satellite still in orbit?
Yes. As a matter of fact, it's still